Hello friends, this is Satish Nikam and we are going to discuss the designing of BCD adder in this lecture. Before going to start the designing of BCD adder, you should know some basic things and that we are going to revise in this lecture. You must know the working of parallel adder, which we have discussed in our previous lecture, and you also must know the working of a 4-bit parallel adder IC, and which we have discussed 74LS283, and this is the block diagram of IC 74LS283, in which we are having 4-bit data A0, A1, A2, A3 and another 4-bit data B0, B1, B2, B3, which is supposed to be added. Before this addition, we have to give the C in input. For this addition, we are getting the result summation S0, S1, S2, S3 and the carry bit. A BCD adder add two BCD digit and produces the BCD digit. You must remember BCD cannot be greater than 9, means 1001 is the last 4-bit number in BCD. Now suppose we consider here one example for the addition one. We have here 7 plus 1 and if we add these two we will get 8. Now how we perform this addition in binary? We got 7 is equal to 0, 1, 1, 1 and 1 is equal to 0, 0, 0, 1, and for this we got the result 1, 0, 0, 1. And if we check here, this nibble, this 4-bit data is not greater than 9, so this is a valid BCD number. But if we take another example, 7 plus 4, the result is 11. Now in binary, how we perform the addition? 7 we have written here and this is the 4 we got, and if we perform the addition we got this result. But in this result, if we check, this nibble, this 4-bit data which we got is more than 9, means it is not a valid BCD. So how we convert it into BCD or how we get it into BCD? By simply adding 6. We add here 6 and we got the result here 0, 0, 0, 1 as a lower nibble, and this is one which we got. We can add here 3 zeros. So we have here valid BCD number. This is 1 and this is 1. This is 11 result which we got here. Again we consider another example. We have to add 9 plus 8 and definitely we got the result 17. Now if we write here 9 1001 and 8 1000, and if we perform the addition we got this result. Again if we check, we got here the carry from this nibble. So definitely this is not a valid number, because it indicates this is 1 and this is 4-bit data, again 1. 11 is the result which is not a valid result. So to make it correct, we have to add 6 in the lower nibble. So after the addition we got this result, and now if we check, this lower nibble is 0, 1, 1, 1, which is 7, and the higher nibble is 1. So definitely the result get matches. Now what is the conclusion of this? If we conclude this, two given BCD numbers to be added using binary rules. Simple binary rules we are going to use, or simple binary adder we can use for the addition of two BCD numbers. If sum is less than or equal to 9 and the carry bit is 0, correction is not required in that BCD. And if the sum is invalid, means if the nibble is greater than 9 or the carry bit is generated, then the correction is required. How we make it correct? By simply, if the wrong result we got, we can correct it by just adding 6 into that nibble. 6 means 0, 1, 1, 0. This number we are going to add. Now we are going to design the BCD adder. For that, we have prepared here the block diagram. And if we check here the block diagram, the first part we will take 4-bit parallel adder IC 74LS283. And if we check here, the first BCD number A and second BCD number B, which we have to add, we have to apply here the input. And we got here the result S0, S1, S2, S3, and we got the carry bit. Definitely here the low carry which we are getting as a in, it must be 0. So when we add this to BCD number, we have to check the result, and if this result is not greater than 9 and the carry is not generated, then that is a valid BCD. So it is not required to add 6 into that nibble. So we will give this output summation from the first parallel adder circuit to the another parallel adder circuit as a input, and we will add 0. So definitely we will get the required result as a S0, S1, S2 and S3. But if in this addition first parallel adder circuit, if we got the result which is more than 9, the nibble is more than 9 or the carry is generated, we have to make the correction. How we make the correction? Simply by adding 6 into the result. For that purpose we have to design here the circuit which will initiate for the parallel adder circuit to be get added with 6 if the input carry bit we got 1 or the result S0, S1, S2, S3, the result we got more than 9, we have to initiate the addition of 6 command to the 4-bit parallel adder circuit. So this is the circuit which we have to design, and these two parallel adders we have already used or we have already discussed in the previous part. In BCD adder circuit, this is the main block which we have to design. Now how we will design this block? In this we are having here 4-bit input S0, S1, S2, S3, and we are having here a single bit output. So for that purpose we have to prepare here the truth table, and as the 4-bit inputs are there, so definite 16 combinations will be there, and which we have written here. Now here you have to remember, when the result is not greater than 9, so why output from your combinational circuit should be 0? If the result is greater than 9, the combinational circuit should generate a signal to add 6 into this result, and for that purpose it should generate 1. So this type of truth table we have prepared. From this truth table we have to find out the expression, and for that purpose we draw here the K map for Y, and we are going to fill the K map here. And when we fill a K map 0 0 0 0 0 0 0 0, then next 0 0 0 1, next 0 0 1 1, and last one 1 1 1 1. This way simply we fill the K map from this truth table. Now we have to form the groups here. We can form here the group of these 4 bits, and another group we can form here of these 4 ones. As we form here the grouping, from these groups we can write down the expression for Y. Now Y is equal to, for the first group, the simple technique is there, the terms which are not changing that we take, and the terms which are changing that we neglect. So in the first group, red group, we can say the expression will be S3 S2, as S1 and S0 are changing, that we neglect. So S3 and S2 is the expression for red group, and for the green group if we check here, S3 is constant but S2 is changing, so we neglect S2. And here if you observe very correctly in this column, S1 is constant and S0 is changing, so we neglect S0. So we take here S3 S1 is the expression for the green group. So we can write down here the expression Y is equal to S3 S2 plus S3 S1, and this is the expression which we got for the combinational circuit which we want to design. Now from this expression we can draw here the circuit, and in this if we check, we are having 2 AND gates and 1 OR gate which we have drawn here in place of our combinational circuit which we have discussed in the block diagram. So here in this block diagram, if we check very correctly, Y is equal to S3 S2, S3 and S2 for the first AND gate, and for the second AND gate S3 and S1, and we make the OR of these two. But when the carry bit is generated, then also we have to initiate the parallel adder circuit to add 6. So we are going to make the OR of this with this OR gate. The carry bit will be high only when, if the carry is generated from this circuit, or S3 S2 is high or S3 S1 is high, and so we have connected this high output to B2 and B1. check here, this B0 and B3 bit is connected to ground, so this becomes 0, 1, 1 and 0. Means when this type of output we got high from your combinational circuit which we designed, the 6 get added with your result which we got. Otherwise the output we got 0, and as we got 0 we are going to simply add 0 0 0 0 with your result which we got. And this way this complete circuit will work as a BCD adder circuit, and here the carry which is generated by from the second parallel adder circuit, that is not supposed to be used, and this is the carry which is supposed to be given to the next nibble for the addition. And this way we have finished the discussion of BCD adder. Thank you.